All right, so we're on to question number 6 on our solubility review. This question's asking us a bunch of stuff, but as with the last one, many of the questions are sort of part of our solution process on a big problem. They just sort of step them out for us here so that we can find our way through with a little bit of guidance. It's not uncommon on the exam that happens, where they actually sort of walk you through it without you realizing what they're doing. So 6 is along the lines of 5. The question's asking us first to write the solubility product equations, which is simply the KSP expression. So for each of our two salts, we want to come up with the KSP expression. Keeping in mind a few details there. Well, first of all, what are our two salts? Well, we've got lead iodide here, and we've got lead fluoride. So I'll write those in different colors just to kind of highlight the differences. Lead iodide, and then our lead fluoride over here. Now, you might be able to go ahead and write your expression without having to write out the dissolving equation. That's totally fine to do if you're comfortable doing that. I'll do that here. If you need to write the equations here along with the salts, go ahead and do that. But for lead iodide, our KSP expression would be our lead concentration. Don't forget the charges times our iodide concentration. Again, charges and a power of 2. On the lead fluoride side, a very similar salt. KSP is going to be our lead concentration times our fluoride concentration squared. Again, leaving out the salt because it's a solid on all KSP expressions. The salt itself will not appear in the denominator or anywhere else in the problem because we've got solids that get left out. So that's our expressions. That's A. All right. For B, they ask us to state the initial concentrations. Now, I think they're doing this to kind of set you up into the next problem a little bit, or the next part of the problem a little bit. But they're up in the problem. They suggest that we've got sodium iodide and sodium fluoride. So it helps to know that sodium iodide is NaI, sodium fluoride is NaF. And the reason that matters is because if these were salts that contained multiple iodides or fluorides, then you would have to say double the 0.0025 molarity, as the fluoride might be twice as much if this was, for example, if this was a solution of calcium fluoride. So my pen is being kind of a nuisance today. If there's a solution of, say, calcium fluoride, then we'd have to double that fluoride concentration since there are 2 of them, but that's not the case here. So for NaF, we're going to get a fluoride concentration of 0.0025. That's my fluoride. 0.0025 molar. For the iodide, it's the same. So our iodide concentration is coming in equal. And what they've kind of done here in these first 2 parts of this problem is they've set us up to recognize that these are 2 very similar salts. So as we go on to C, they're going to ask which will precipitate first. And they're going to ask us to justify it. It's going to be important to know that you should always be able to justify your answer, because they're typically not going to give you just a heads or tails kind of a choice here and get a point for it or anything on an AP exam. But which will form first? The less soluble one will. And the K values that they gave us up above, the K value for our lead iodide, 9.8 times 10 to the negative 9. For our lead fluoride, 3.3 times 10 to the negative 8. We usually can't simply go to KSP and say that that's enough to decide which one's soluble, but we can when the 2 salts are the same type of salt. In this case, this is a 1 to 2 salt. This is a 1 to 2 salt, so we've got a fair head-to-head comparison. And we have iodide concentration and fluoride concentrations that are equal. So essentially those come in and would give us a fair head-to-head comparison. So yes, in this case, because we have 1 to 2 salts and we have a pre-existing ion concentration of iodide and fluoride that's equal, we can, for C, simply say that lead iodide will precipitate first because it has a lower KSP. It doesn't ask us for a reason, but we should say so. Lower KSP, then lead fluoride. Same ion ratio in our salts, which makes it fair to compare them that way. And equal concentrations of fluoride and iodide. So those are all evidence that tell me that these are very apples-to-apples comparisons. We can really put these 2 salts head-to-head against each other and compare them a little bit more evenly than often is the case because they're so similar. For D, it wants us to figure out what volume of lead nitrate solution will be required for the first precipitate to form. We're suggesting that that's lead iodide. Notice here they're asking us for the volume of lead nitrate solution. Up in the problem, we're adding, and they tell us a very specific amount here, we're adding from a 1 mole per liter solution of lead nitrate. So if you kind of imagine what's going on here in this scenario, we would basically have, say, a beaker, right, a 1 liter beaker. And I'm talking now about this. This is a 1 liter beaker here. In that are iodide and fluoride ions in equal parts. And to that, we're going to be adding this solution here of lead nitrate. So I've got my lead nitrate solution, 1 mole per liter. And I'm going to be adding that drop at a time in order to form here some precipitates down here in the beaker. And they're asking me to figure out here on D how much lead nitrate, what volume of that solution will be added before the first precipitate reaches its saturation point and begins to form. So for D, they want us to take the KSP values, or the KSP expression, for lead iodide and figure out what lead concentration is going to be necessary. And that's the start of our solution. So for lead iodide, we have a K value of 9.8 times 10 to the negative 9. That's the first precipitate to form. And the lead concentration required to do that, we have to figure out. The iodide concentration is already there, and we just wrote it down on part B, so we know that to be 0.0025. And we need to square that quantity because of our expression setup. If we go through into the algebra, our lead concentration required to reach that expression's maximum, right? Our lead concentration at that point will be 0.0025 moles per liter of lead. Right? The question then, oh, pardon me, I made a mistake. It was 0.0016. I looked at the wrong line on my key here. So the lead concentration required to hit that threshold and begin precipitating it will be 0.0016 moles per liter. Now, that's moles per liter, right? Concentration that we're going to have to reach. And that's the concentration we'd have to reach in here, 0.0016 mole per liter lead. And at that point, the concentration will be enough to start forming precipitate with the iodide at that moment. Okay, well, the question asked us not what the lead concentration will be, but what volume of the available solution will be required to get to that point. So it's a relatively simple matter of, we're using, in a 1 liter container, we're mixing this into a 1 liter beaker, so we're going to need 0.0016 moles of lead ion. And we're working with a solution that we know contains 1 mole of lead for every 1,000 milliliters. All right, that's the available solution. We wrote that earlier. I sort of had that marked out as the concentration of the lead here in an orange color. So that's that concentration from up here in our solution that was given at the beginning, 1 mole per liter of lead ion. And the nitrate's not important, of course, because nitrate's a spectator. So we're going to need 1.6 milliliters of the lead solution to make that first precipitate form. It's mostly stoichiometry after a little KSP math. It's stoichiometry to figure out how much of that solution will be required. So 1.6 milliliters, drip, 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 up to 1.6 milliliters, and you would have the first precipitate forming, lead iodide. Question E asks us to do the same thing, but figuring out what would be required in much the same way to get the second precipitate to form. So for that one, we're going to use a KSP value, 3.3 times 10 to the negative 8 for the lead fluoride, and figure out what lead concentration would be required alongside the 0.0025 moles per liter fluoride concentration. Pardon me, that's a 2. Okay, that's already in the solution, already in the beaker. And so our lead concentration for this one, if you go ahead and plug and chug and do the math, should come up with a molarity of 0.0053 moles of lead per liter. Again, I'm writing it out as moles per liter because we're going a little further with it. Typically, that capital M is enough for molarity. Now, if you're following along and you're not punching these into your calculator to make sure that you can get these answers, that's trusting that you'll be able to do it when it comes time to do it for real. That's perfectly fine if you're confident in that, but I would say definitely pause, feel free to pause, make sure you can punch these calculations in and get those lead concentrations that we've gotten now in the last 2 parts here. Now, we're not quite done with E, but much like the last one, in a 1 liter beaker, this would mean that we would need to have present 0.0053 moles of lead. And we're still adding those lead moles, all right, from the same stock solution of lead that contains, for every 1,000 milliliters, 1 mole of lead ions, which means I'll need to add 5.3 milliliters of lead solution to get that second precipitate to form, And that makes sense, because that would mean we need to add more lead to get the second precipitate to form, and that's logical. That's why it's second, right? Because we have to add more. For part F, they're asking us more or less to figure out how effective was the separation. Now, it doesn't say that, but it is saying in F, when the second precipitate begins to form. Well, what is that? We just said the second precipitate is lead fluoride. When that begins to form, what concentration of halide ion that remains from the first precipitate will still be there, unprecipitated, still be dissolved? Well, the halide ion from the first precipitate is, they're looking for then the iodide concentration, because the first precipitate was lead iodide. The halide, a halogen element, is the iodine here. And so how much halide would still be free? And so what we need to do is we need to take the lead concentration that we just determined on part E, bring it down and put it in to the KSP expression for lead iodide. So for lead iodide, one more time, the K expression, 9.8 times 10 to the negative 9. A lead concentration then, again, bringing that value down from up here. When the second precipitate begins to form, this will be the lead concentration. So 0.0053 molar lead. How much iodide will still be in solution at that point is a matter of leaving that as our unknown to solve. Take a minute if you'd like, pause, figure out what this iodide value is by your own algebra, and then bring it back to life. If you're back and you've done that, the calculation that you should come up with for iodide concentration here is 0.0014 molar. That's the ending concentration of the iodine, rather not ending concentration, but that's the remaining concentration of iodide when the lead fluoride begins to precipitate. Often these questions would ask us to consider then what percent of the original then is still present. Well, this is the remaining amount. How much was originally present? Back in the original question, they told us that the original amount was 0.0025. So really, most of it's still there, right? We've got over half of the original still left. In fact, this represents 52% of the original. I think I got that right. 56%, pardon me. 56% of the original is still there. So that's actually not a very effective separation at all. We would want more of 90, 95, 99% of the one ion to be precipitated and not remaining when the second one begins to form. That's the idea of these, as selective precipitation, to isolate one ion from another by precipitating it out first selectively. Okay, so that's the idea for 6. Let's take a look at 7. 7 really is just asking us to do, in all intents and purposes, it's just asking us to do the very last thing that we did on number 6, and only that. So to accomplish that, we had to do, really, if you look back at 6, we had to do two things. We had to do E, to figure out how much lead would be added to precipitate the second solid, and then bring that value down and plug it into the second part of our calculation there on F. So that's what we'll have to do here for number 7. We'll have to figure out how much will have to be added to start the second one precipitating, and then turn around and use that again. So which one will precipitate first? That's kind of the thing to think about here. And which one will precipitate second? Well, in this instance, we can look at our two salts here and recognize that the ones they're comparing us, having us compare in this case, are silver chloride, AgCl, and silver chromate, Ag2CrO4. Typically, the formulas would be provided on an AP question, so if you're not comfortable with those at this point, we very rarely see a place where the formulas aren't just flat out given. But the key then with these two salts is that we can't compare them as easily head to head, right? Because even though we have both KSP values, here's silver chloride, right, and here's silver chromate, we can't look at those and eyeball them and say, oh, silver chromate will precipitate first because it has a lower KSP value. It's not fair to do that in this case because we have salts with different ratios. Our silver chloride is a 1-to-1 ratio, so the molar solubility, in this case for this, KSP, I don't want to put that under precipitate first, but the KSP for silver chloride will be an x squared sort of an expression, right? Because both silver and chloride will be x. Meanwhile, in the silver chromate, when we dissolve these into solution, we're going to have 2x silver and 1x chromate. And so the KSP expression for that one sets up as 2x quantity squared times x, times x. So this is one of those 4x cubed salts. So in the end, we can't compare these easily head to head because they have different expressions, right? They have very different ratios. If I go ahead and figure this out, though, if I go ahead and figure out what those x's actually are, and that's the fair way to sort of put these up next to each other and decide which one will precipitate first. If I go ahead and figure out the x values, I'm going to find that for the silver chloride, which is everything I'm doing here in blue. For silver chloride, the x value is 9.83 times 10 to the negative 8 moles per liter. So that's the amount of silver necessary to precipitate that one. And then the second one to precipitate then will be our silver chromate. And then we kind of know that is that the x value I would figure out for that is actually quite a bit less, 7.89 times 10 to the negative 6 moles per liter silver necessary to precipitate that one. And again, the way I did that is I plugged in the KSPs that were given to these expressions up at the top, and then figured out what x would be, just by a basic algebra from there. So because the silver chloride has a smaller molar solubility, it will precipitate first here. And so the first precipitate will be that silver chloride. Even if they didn't give us this last sentence, right, that's how we would figure it out. And you might have been looking at it and saying, wait a second, Pleth, just read that last sentence, buddy. We don't have to do all this work. But to point out, they don't typically necessarily have to give us that last sentence. They might just say, what's the concentration of the first when the second one begins to form? And so here they sort of suggested here, and we've proven it, that the chloride will in fact precipitate first, and the silver chromate will begin to precipitate then later, or second. And we've confirmed that by our math. Right? So what are the questions asking? What amount of silver will it take to get the second one to precipitate? And then, when that's the case, how much chloride will still be left? So we're going to start actually with the second one. And our KSP value for that second one, given at 1.12 times 10 to the negative 12, is going to be equal to silver concentration squared. That's what we're trying to find. So silver concentration squared. And then chromate concentration, given in the problem, at 0.018. How much silver will it take to get that silver chromate to precipitate? Do the math, do the algebra. Feel free to pause me if you like. And you'll find out hopefully that the silver concentration to get that will be 7.89 times 10 to the negative 6 moles per liter. To cause silver chromate to precipitate second, later. Okay. When that happens, how much chloride will still be available? So we're actually going to bring that over to the other side with silver chloride. Bring down the silver chloride's KSP value, 1.77 times 10 to the negative 10, given the problem. The silver concentration at these conditions, we're going to bring over and pop in right there, is 7.89 times 10 to the negative 6. In this expression, we don't need to square it, right, because silver is just a 1-to-1. But the chloride concentration that remains there is what we're really after. How much chloride will still be available and dissolved in the solution when the second precipitate begins to form? Take a minute if you wish to pause it and come back and see what you come up with. And if you do that, hopefully you come up with an answer of 2.24 times 10 to the negative 5 molar chloride. That's very, very small. That's our answer. That's what they're asking us for. Pardon me. Got a little slippery here screen. That's the answer they're wanting. What's the concentration of chloride as the second one begins to form? And that happens when silver reaches this threshold we found first here in green. But just to kind of follow up like we've done in the past, how effective is this separation? This is the remaining amount of chloride, right? How much was there at the beginning? Originally, we had 0.018 molar chloride. And now we have, what is it now? How much remaining? 0.0000224 molar. Boy, we started out with 0.018. We've got very, very, very little of that left. In fact, if we divide and take that times 100, we'll find that that comes out to be only 0.12% of the original is still there, which means we've basically lost or precipitated 99.88%, which is effectively 100% precipitated. That's very effective precipitation for this particular ion with silver as the thing that we're adding to do that. So this would be a very effective way of separating chloride from chromate by their solubility differences with silver. So that's number 7. Hopefully that helped you out a little bit. These questions are complex. There's a lot going on. It's often just a matter of taking the information that you're given. If you have 2 salts, setting up 2 equations, 2 K expressions, maybe even 2 Rice tables when the conditions are such that that's required. But at least start with the expressions, figure out what you know, figure out what you're asked for, sort of identify that and put a question mark on it. In this case, they wanted to know that concentration of chloride, so we kind of had to recognize that we were going to look for a chloride, and that must mean we'd have everything else available in order to do that, or else be able to get there by a pre-calculation like we did here. If you have other questions with these problems, see me outside of class or even ask them in class. Good luck with any upcoming test you might have. This year, that's coming up next week, and we'll see you when I see you. Thanks for listening.